counting number n, b to the nth power means to multiply b times b times b times b an n number of times. That's what this means. So notice that we have b to the nth power, and then we multiply b times b times b times b dot 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 all the way out here. And there are n number of times for which we do this. Okay? So we refer to b to the nth as the power, the nth power of b, or b raised to the nth power. And we call b the base and n the exponent. So, for example, what this is saying is that 3 to the 4th power does not equal to 12. Right? Most common mistake. We don't multiply those two things together. Does not equal to 12. What 3 to the 4th means is that we're going to multiply 3 times 3 times 3. And when do we stop? We do it 4 times. Right? So this tells you how many times to multiply that base. 3 times 3 times 3 times 3. 4 different times. And so 3 times 3 is 3 times 3 is 9, times 3 is 27. So the final answer is going to be 81. Okay, so this is a rule. This is a list of all the different properties that we're going to have to focus on. So there is 1, 2, 3, 4. There's 5 different properties that we're going to look at. So the first thing I want to do is kind of look at various examples or an example for each one of these to justify why these rules are true and what they really mean. So let's focus on this first one. B to the m times b to the n is equal to b to the m plus n. Notice that in both cases I have an exponential, in this case we have an exponential number times another exponential number. Then they both have the same base of b. And this is saying that when you have a situation like this, all you have to do is add the exponents. All right, so let's look at why that is. This is the product property of exponents. So for the product property of exponents, consider the following. For example, if I have 3 to the power of, well, let's do the one. How about 2 to the power of 3 times 2 to the power of 4? Okay, so if I wanted to expand this, this would be 2 times 2 times 2. And if I wanted to expand this one, it would be 2, 2, 2, and 2. 1, 2, 3, 4. Notice that we have a multiplication there. And so we'd still have a multiplication there. And so at the end of the day, I have 1, 2, 3, 4, 5, 6, 7 copies of 2. So this is 2 to the power of 7. That makes sense? Good? Good, good? Okay, so we just multiply that out. What is that? 2 times 2 is 4, 8, 16, 32, 64, 128. Good? Okay, well this property says that if we have a situation like this, an exponential number times another exponential number with the same base of 2 in this case, then what you could do is just add the exponents, and that makes sense here. So for instance, you could have written this as 2 to the 3rd power times 2 to the 4th power, which is 2 to the 3 plus 4, or 2 to the 7th power. Right? That's what that's describing, and then again, that's just equal to 128. Good, 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 good. Okay, so the purpose of these properties is for you to be able to do things faster, right? They're nice little shortcuts. We want to be able to use the shortcuts. I'm just going to justify why the shortcuts are there, but my intention is not for you to do it the long way. So I'm just showing you the long way once or twice so you can see where the shortcuts come from, and then you're supposed to use the shortcuts. So no, you don't have to do it this way. I'm expecting you to do it that way. As you get practice some of these things, you'll see you get good at it and you'll go through it faster. Okay, so that's that top one, that top property. Okay, so that was the first property. What about the second property? This one says that if we have two exponential numbers being divided, where the exponent in the numerator is an m, and the exponent in the value in the denominator is an n, then we can simplify this fraction as b to the power of m minus n. So we subtract the exponents. That's what this is saying. For example, if we had b to the power of 7 divided by b to the power of 4, then we can expand the numerator. That's just going to be b times b times b times b times b, 1, 2, 3, 4, 5, 6, 7, all over b, 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 1, 2, 3, 4. I know these guys cancel. Oops, I went too far. So 4 of these cancel with 4 of those. And these guys are the survivors. So I end up with b to the power of 3, right? There are 3 b's that survived. That's the long way of doing it. And the shortcut tells me that if I have b to the 7th over b to the 4th, this is equal to b to the 7th minus 4, which is equal to b to the 3rd power. Good? Questions? Okay, so the pattern is, the pattern will hold as long as they both have the same base, b. And that base could be all kinds of things. So for instance, it could be something like 2x plus 5 raised to the 4th power divided by 2x plus 5 raised to the, well, let's make this to the 5th power to the 3rd power. It's the same thing, right? Instead of just a single letter b, now I have this little equation, which is pretty ugly, but at least they're both identical. 2x plus 5, 2x plus 5, they're both being raised to some exponential power. So I know that that ugly thing could at least be reduced as 2x plus 5 raised to the power of 2. Following the exact same principle, right? The same rule. Does that make sense? Good? The same happens with the exponent, right? Another thing we could have is just a single letter raised to, say, an equation like 2x plus 5 divided by x to the power of 4 minus 6x. Ooh, no, let's not do an x and an x. That was ugly. How about y? 2y and a y there. That's good. Okay, so again, really ugly looking, but at least they both have the same base. And I know from that rule that all I have to do is subtract the exponents. So I know that this is going to turn out to be one big happy x to the power of this minus that. That'll be 2y plus 5 minus, let's make some more room there, minus 4 minus 6y. And be careful to make sure to put this guy in parentheses because this subtraction applies to the whole thing. So we end up with x to the 2y plus 5 minus 4 plus 6y, which is equal to x to the 8y plus 1. Okay, so you see how here we started with just a very simple b to the 7th, b to the 4th. We can expand it all out. Obviously some stuff cancels. But from that we extrapolate this very straightforward rule that all we have to do is subtract the exponent from the numerator minus the exponent from the denominator as long as the bases are identical. Good? And then we can kind of see other patterns in which it works. Any questions? No? 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 Notice that one of the conditions is that b can't be 0. Right? The original statement says this is true as long as b is not 0. And that makes sense because one of the founding principles in math is thou shalt not divide by 0, right? So we always have to keep that in mind that b does not divide by 0. Alright, moving on to the next rule. Okay, so the third rule we're going to look at is this one. In parentheses we have bc raised to the power of n. Which then is equal to b to the nth, c to the n. This is raising a product to a power. And it almost looks like a distribution of exponents. You can think of it that way. You just have to be careful on exactly what this means. So let's look at an example. So what this property is saying is if we have a multiplication, like for example 3x raised to the power of 4. Right? This looks like that. The b is a 3, the c is an x, right? So it's a multiplication inside parentheses being raised to a power of 4. Well, by definition of what that means, it means that we multiply this thing by itself 4 times, right? If it was just like b to the 4th, it would be b. But this time we have 3x raised to the 4th. So we got to multiply this thing by itself 4 times. So this is 3x times 3x. Times another 3x, times another 3x. 1, 2, 3, 4 copies of 3x. Good? Well, everything's being multiplied, right? And inside the parentheses, everything's being multiplied. So do we really need those parentheses? Not really, right? 3x, 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 3x. Everything is being multiplied. And one of the great properties of multiplication is that we can reorder it any way we like. So why not group together all the 3's and then all the x's? Good. And then this can be rewritten as 3 to the power of 4. And this can be rewritten as x to the power of 4. So we can rewrite this whole thing as 3 to the 4th x to the 4th, which is what this property tells us we can do. Which almost looks like a nice, straightforward distribution of exponents. Good? So again, I don't expect you to do it this way, the long way. This is too much work. I'm just showing you why the rule works. So let's apply that rule. The rule says that if we have 3x to the power of 7, well, this is just going to be 3 to the 7th x to the 7th. Right? It's sort of a distribution of exponents. Notice that this requires this to be multiplication. The things that are inside the parentheses have to be multiplied. If we throw in a wrench like 3 plus x to the 7th power, that does not equal 3 to the 7th plus x to the 7th. Unfortunately, that's not the way it works, right? If you recall, if this had been like a 2, 3 plus x squared, we have to FOIL that, right? So that's going to turn out to be something with 3 terms, and we get a middle term of 3x. 3x and then another 3x, so 6x. At any rate, this is going to turn out to be a lot uglier than that. So it doesn't equal that. Okay, so keep that in mind. And also, what if it was just a little bit more complicated? Instead of just having powers of 1, we can also have powers of some other value there, and the property holds. So for instance, if I had 2 to the power of 4 and p to the power of 3 and w to the power of 2, all of it being raised to the 5th power, then if we do it the long way, okay, the long way would be to repeat this by itself 3 times. 2 to the 4th, p to the 3rd, w to the 2nd, times 2 to the 4th, p to the 3rd, w to the 2nd. 1, 2, ugly. Oops. 2 to the 4th, p to the 3rd, w to the 2nd. 1, 2, 3, 4. See why we need rules and shortcuts. Well, that's ugly, but okay. We had 5 copies of this whole thing. So we copied it 5 times. And now, just like before, everything's being multiplied, so we don't really need the parentheses. And just to save some time, we also know that we can regroup them. So I know I'm going to end up with 2 to the 4th times 2 to the 4th times 2 to the 4th times 2 to the 4th. 1, 2, 3, 4, 5, just following the 2's. Then p to the 3rd, p to the 3rd, p to the 3rd, p to the 3rd, p to the 3rd. 1, 2, 3, 4, 5 of them. 1, 2, 3, 4, 5 of them. And then finally the w's. W to the 2nd, w to the 2nd, w to the 2nd, w to the 2nd, w to the 2nd. 1, 2, 3, 4, 5. And going back to rule number 1, if I have a multiplication of a bunch of exponential numbers with the same base, what can I do to the exponent? 2 to the 4 plus 4 plus 4 plus 4. 1, 2, 3, 4, 5. All right, well, what's that going to be? 4, 8, 12, 16, 20. So that's going to be 2 to the 20th power. And what about the p's? P to the 3 plus 3 plus 3 plus 3 plus 3. That's going to turn out to be p to the 1, 3, 6, 9, 12, 15. And finally the w's. W to the 2 plus 2 plus 2 plus 2 plus 2. 1, 2, 3, 4, 5. So that's going to end up being w to the 10th power. Okay, well, the shortcut would have been a lot easier, right? Hopefully you never write all this work ever again, and hopefully I never write all this work ever again, because the shortcut's really easy. All we have to do is distribute the exponent. Notice that it requires all of this to be multiplied, but as long as it's being multiplied, then all of this will hold true, which means I could have just multiplied 2 to the 4 times 5, or actually, I guess I'll do it this way. 2 to the 4th raised to the 5th power, p to the 3rd raised to the 5th power, w to the 2nd raised to the 5th power, which then becomes 2 to the 20th, when I well, I guess I'll write it out. 4, 5, times p to the 3 times 5, and then times w to the 2 times 5, right, up in the exponent. And then finally, 2 to the 20th, p to the 15th, w to the 10th. Okay, so you don't even have to do these middle steps once you get comfortable with it. It's very easy to go from here to the final answer. Any questions? So that's this property here. The next property is very, very similar. We have a division of some kind, b over c, raised to the power of n. And so there's a distribution of exponents once again, just very, very similar to the one before. So for instance, if I have 3 over 2 raised to the power of 4, this is 3 over 2 times 3 over 2 times 3 over 2 times 3 over 2. 1, 2, 3, 4 times. That's what this guy up here tells me. It's got to be 4 copies of it. And so this can be one big happy fraction of 3 times 3 times 3 times 3 all over 2 times 2 times 2 times 2. Right? I can multiply 3 times itself 4 times, 2 times itself 4 times. And so this can be written as 3 to the 4th power divided by 2 to the 4th power, which is again a very straightforward distribution of the exponents. Good? Good? Okay, so then if I wanted to take advantage of that shortcut, I could use it in this way. How about if I had 3 squared divided by b to the 3rd power, all of it raised to the 5th power? Well, this is saying that it'll be 3 squared times 3 squared times 3 squared times 3 squared, 1, 2, 3, 4, 5, all over b to the 3rd, b to the 3rd, b to the 3rd, b to the 3rd, b to the 3rd. Too much work, right? Or we could just recognize that all we have to do is multiply these. So this is equal to 3 to the 2 times 5, all over b to the 3 times 5, or 3 to the 10th power all over b to the 15th power. Good? Good, good, good. So now the question becomes, well, should we leave that alone or should we actually multiply it? 3 times 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 3. Should we leave it alone or should we multiply it? Well, there's no real good answer to that. The guideline is if it turns out to be a small number, you should multiply it. Usually it's under 1,000. So if it turns out to be under 1,000, it just looks nicer to see the number. Like if the answer is 802 divided by b to the 15th, that looks better. But if this number turns out to be too big, then it just really doesn't look good, right? What is 3 to the power of 10? How many digits are in that number?
5.
It's a 5-digit number?
Yeah.
3 to the power of 10 is 59,049 over b to the 15th. Okay, so what looks better? 59,049 divided by b to the 15th, or 3 to the 10th over b to the 15th? You know, okay, maybe it's a little close. I think at this point it looks better that way. But exponential numbers can quickly get out of control, so this could easily be a number that's so big that it's very cumbersome to even write it down. So if it's under 1,000, multiply it out and give me the expanded value. Otherwise, just leave it alone as an exponential number in its most reduced form, if you can reduce something. Okay, we're down to the last property we want to look at. B to the m raised to the nth power. This one looks an awful lot like the first one, but just a little bit different. So, for example, if I had 3 to the 3rd power, well, let's make it 3 to the 2nd power raised to the 4th power. right? By definition, describing this means that there will be 4 copies of this. So that would be 3 to the second times 3 to the second times 3 to the second times 3 to the second. 1, 2, 3, 4 of them. And now each one of these is really a 3 squared, 3 squared, 3 squared, 3 squared. So 2 copies of 3 from there, 2 copies of 3 from there, 2 from there, and 2 from there. So at the end of the day, how many 3's do I have? 3 to the 8th power. 2 from there, 4, 6, 8 copies of 3. That should be the answer for sure, right? Okay, so what should we do with the 4 and the 2? Multiply them, right? That's what this property tells me, that if I have an exponential number raised to another exponent, the shortcut will be to just multiply them together. Okay? And so this is 3 to the 2 times 4, which is equal to 3 to the 8th power. Good? Questions, comments, issues? This is not to be confused with the very first property. So remember that in the first property, if we had 3 to the second times 3 to the 4th, that looks an awful lot like this one, but it's a little bit different. That one is the first property, which tells us that we should add the exponents, which is 3 to the 6th power. Right here we have 2 copies of 3 times 4 copies of 3. And in all, we should have 6 copies. Whereas this one says we should have 4 multiples of this thing. And we end up with 8 of them. Examples. What about the first one? How do we simplify this guy? This one should be really straightforward. 2 times b squared c to the 3rd, all of it raised to the 5th power. There's nothing we could simplify inside the parentheses, right? These bases are different. I can't add these somehow. I can only add the exponents if they had the same base b, but they're different, so I can't simplify those. So the only thing I can do is do a distribution of the exponent. So I end up with 2 to the power of 5 times b to the power of 10 times c to the power of 15. Right? That's all you really have to do for this one. So 2 to the power of 5, what is that if we expand it all out? 2 times 2 times 2 times 5 times, what is it? 32. So our final answer is 32, b to the 10th power, c to the 15th power. Good? Pretty easy. Okay. That's what we get here. 2 to the 5th, b to the 10th, c to the 15th. We ended up multiplying the exponents. Let's look at the second one. So we have this times this. Everything's being multiplied, right? So I don't even really need the parentheses. So I could get rid of all the parentheses and group together the various terms. So I have 2 times 3 makes it 6. And then I have a b to the 3rd and a b to the 6th being multiplied. What's that going to turn out to be? B to the 9th power, right? We add the 3 and the 6. And then we're going to have c to the power of 6. We're going to add those exponents as well. So we'll get this. Okay, so the parentheses there made no real difference. I could just regroup them, get rid of the parentheses. I can reorder them in any order I like. And I can bring together the 2 and the 3 to give me a 6. And then the b's, I can bring them together to give me a b to the 9th. And then the c's, I can bring together to give me a c to the 6th power. Good, 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 good. Okay, what about number 3 here? Well, the 3 and the 12th reduce, right? And then I have...
You subtract b to the 7th and b to the 2nd.
Good, so you get b to the 7 minus 2, or just b to the 5th power. And what about the c's? C to the 6 minus 5 is just c. Okay, so we end up with something that looks like this guy. So the 3 and the 12 reduced to give you a 4 down in the denominator. And then the b's were brought together as b to the 7 minus 2 to just give you b to the 5th power up in the numerator. And then the c's, we had c to the 6th
divided by c to the fifth, so we subtract the exponents, and so we end up with just c. Okay. What about the fourth one? Okay, so we have a choice here. We could distribute first if we wanted to. We'd end up with 24 to the fourth power, and then b to the 28th power, and then c to the 32nd power. And then in the denominator, we would end up with 16 to the fourth power, and b to the 8th, and c to the 20th, and d to the 12th. That's how we could distribute this 4 through every one of these terms in the numerator and denominator. But then we'd end up with larger values, right? C to the 32nd, b to the 28th, and also 24 raised to the 4th. That's ugly. So I don't recommend that. I think it would be much easier for us to simplify what's inside the parentheses first, reduce it as much as we can, and then deal with this exponent over here. Okay? So when we reduce them, what do we get? This is 8 goes into here 3 times, 8 goes into here twice. So I know this is just going to be 3 over 2. And what about the b's? B to the 5th power up in the numerator, c to the 3rd power up in the numerator, and then there's this d to the 3rd power in the denominator, and then we distribute the powers of 4. So let's see. The 24 and the 16 reduce to a 3 over 2. The b's reduce, so they have b to the 7 minus 2 to give you b to the 5th. C to the 8th minus 5 to give you c to the 3rd. And in the denominator, we just end up with this d to the 3rd. Nobody wanted to play with that, so we leave that there. Raise to the power of 4. And now we distribute the exponents again. So 3 to the 4th, b to the 5th raised to the 4th, c to the 3rd raised to the 4th, 2 to the 4th, d to the 3rd raised to the 4th. We get these guys, which we know we multiply. So we know we end up with 81. That's 3 to the 4th is 81. And then b to the 5th raised to the 4th is b to the 20th, since we multiply these two numbers. Then we multiply these two numbers to get that one, c to the 12th. Multiply these two to get d to the 12th. And then 2 to the 4th is also 16. So there's our final answer. Any questions? No? 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 Very important to notice. 3b squared and 3b in parentheses squared are not the same thing. They're not equivalent. Why is that? Well, this one over here means this. We repeat the b twice. The square applies to the b. So it's 3 times b times b. Whereas in this case over here, this means that we multiply 3b times 3b, right? The squared applies to the whole thing. That's why we put parentheses around it. And so when we multiply 3b times 3b, we end up with 9, right? 3 times 3, 9b times b. And this is definitely not the same as that. So these two expressions are not the same. So the moral of the story is if you want the square to apply to the whole thing, you better put parentheses around the whole thing. Otherwise, by default, it only applies to the number immediately next to it on the left-hand side or variable immediately next to it on the left-hand side. Likewise, for the same reason, this does not equal to this. Right? It's the exact same reason why. So on the left-hand side, I think it's exactly what you think it is. We multiply -3 times -3. And so on the left-hand side, this is just going to be equal to +9. Okay? On the right-hand side, we separate this as -1 times 3. Right? -1 times 3 is -3. And so now this squared only applies to the 3 and not the -1. So this is -1 times 3 times 3. And so we end up with 9. And then on the right-hand side, it equals to -9. So no, they are not the same thing. Good? For the same reason. We just by default assume that the exponent only applies to the number immediately to the left. And if it's a negative this way, then we separate it this way. Because if you wanted it to apply to the negative, well, you should have put parentheses around it. So a little bit ago, when we were looking at the division rules, we had something that looked like this. Say b to the 5th power divided by b to the 3rd power,
which is b, 1, 2, 3, 4, 5, all over b, 1, 2, 3. A bunch of these guys cancel. We end up with b times b, or b squared, right? That was back when we were looking at the division rule for exponents this way. And so we found that our shortcut rule, what we want to use, is that when we have b to the 5th power over b to the 3rd, this is equal to b to the 5 minus 3, which is equal to b squared, right? That's the rule we want to stick to. And so the rule was given as b to the m power over b to the n power equals to b to the m minus n. Good, good, good. Okay, but what if it was a little bit different? What if these guys were this way? What if we had b to the 3rd power up there and b to the 5th power down there? Then when we expanded, we'd have 3 multiples of b up there. 1, 2, 3, 4, 5 multiples of factors of b down there. 1, 2, 3, these guys cancel. We'd end up with 1 over b times b, which would be 1 over b squared, right? So this is definitely how this reduces, right? Forget the shortcuts and all that. I know that this expands this way, this expands this way. A bunch of stuff cancels. We end up with 2 factors of b down in the denominator. I know the answer should be 1 over b to the 2nd power. However, if we use our little rule, b to the 5th, we end up with b to the power of 3 minus 5, this one minus this one, which is equal to b to the negative 2 power, which is kind of a weird thing, right? Negative exponents. So to fix it, we define these two things to be the same. Defined as the same. That's how we define them. Okay? So b to the negative 2 power is equal to 1 over b to the positive 2 power. Bringing them together, b to the negative 2 equals to 1 over b to the positive 2 power. Now there's nothing special about the fact that the difference between the 2 was a negative 2. So that property holds true for any value of the exponent. So if we had b to the negative 8th power, I know that that's going to be equal to 1 over b to the positive 8th power, for instance. So the general rule is going to be that one. B to the negative nth power is equal to 1 over b to the positive nth power. Okay, so that's how we define it. That's how we eliminate this negative in the exponent. We define it to be equal to its reciprocal, where we take the reciprocal and then make the exponent positive. Good? Good, good, good. Okay, so that's our rule. You just got to keep in mind though, going back to the golden rule or the guiding principle in math, you cannot divide by 0. So just keep that in mind, that's a condition. As long as b doesn't equal 0, this will always hold true. Good, 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 good. Well, what if we had... So let's explore that a little bit. What if we had a negative in the exponent in a fraction that was already in the denominator? So let's say I had this, negative 4. Right? How do we simplify that? Well, what we're going to do is we're going to just kind of focus our attention on the denominator. So this is equal to 3 over, and now to get rid of that negative in the exponent, in the exponential number in the denominator, we rewrite this as 1 over x to the positive 4, still staying in the denominator, right? So this is still one big happy fraction there, where this is in the denominator, so we leave it in the denominator. Okay, and now how do we simplify that? Well, this will be equal to 3 times the reciprocal of that, which gives you x to the power of 4. Okay, so 3 over x to the power of negative 4 is equal to 3 times x to the power of positive 4. Okay, so a little pattern starts to appear. If I started out life with a negative in the exponent in the numerator, like if I had x to the negative 4 divided by 3, if this was the original question, well, this is equal to 1/3 times x to the negative 4, right? I can just kind of separate in that way. And we just saw that in order to get rid of this, all we have to do is take its reciprocal, 1/3 times 1 over x to the positive 4. So it's its reciprocal, but then we make the exponent positive. And so our final answer is going to be 1/3 x to the positive 4. Okay, so the pattern should be this. If we have a negative in the exponent, and we want to get rid of the negative in the exponent, then if the exponential number starts out life in the denominator, then we move it up to the numerator and make it a positive exponent. If it starts life out in the numerator already, then to make it positive, we just move it down to the denominator and make it positive. Notice that this is not a reciprocal though, because in both cases the number stayed right where it was. I wasn't just flipping this whole fraction, all of it. The 3 started in the denominator and it ends in the denominator. The 3 started in the numerator and it ends in the numerator. We're just taking the reciprocal of the individual values with a negative exponent. Good? Good, good? Okay, so this idea of dealing with a negative in the denominator is given by this. So 1 over b to the negative n is equal to b to the positive n. Good. Alright, so let's do a more interesting example for this one. So let's combine those two properties for this example. W to the second, p to the negative third, b to the fifth power, all over a to the negative 11, b to the positive 8, and k to the negative fifth power. Okay, so my intention is not for you to do it the long way like I'm about to do. I'm about to show you why the shortcut is really, really easy in order to do this one. Okay, so what I'm going to do is I'm going to apply the properties to each one of these individually. And so in order to get rid of that negative there, I got to take its reciprocal and make it a positive exponent. So I'm going to do that for each one of these. So this is equal to w squared, 1 over p to the third power, and then b to the fifth power. I guess I could just put little ones there. And all of that is up in the numerator. In the denominator, I end up with 1 over a to the 11th power, b to the 8th, and then 1 over k to the 5th power. I guess I can put a little 1 there. Right, so now in the numerator, this ends up being one big happy fraction of w squared b to the 5th all over p to the 3rd, all over b to the 8th, a to the 11th, k to the 5th. Still one big ugly fraction where there happens to be a fraction in the numerator and a fraction in the denominator. And so finally, this turns out to be this one, this fraction, times the reciprocal of that one. So we get w squared b to the 5th power divided by p to the 3rd times a to the 11th, k to the 5th, all over b to the 8th. Okay, and then we just multiply them together and that's our answer. Okay, so this is the long way. We don't want to do it that way. But look how easy the shortcut is. B to the negative 3, p to the 5th, all over a to the negative 11, b to the 8th, k to the negative 5th, k to the 5th. Does that mean? That's not mean. The shortcut is this. If the exponent is positive, then we leave it alone. Right? So w to the second is up there. There's a b to the 5th up there. There's a b to the 8th down here. I didn't notice I used the same b. Anyway, then down in the, so now this guy has a negative in the exponent. So it started life in the numerator. We just move it down to the denominator and make it a positive exponent. This guy started life in the denominator with a negative exponent. So we move it up. A to the positive 11th, and this guy, move it up, so k to the positive 5th. And that's that step over there. So at this point, this equals to that. And I didn't have to do this whole crazy thing in the middle, right? The rule is very straightforward. If it has a positive exponent, leave it where it is. If it has a negative exponent, then you just move it from numerator to denominator or denominator to numerator and change the sign. Good. So we're almost done. The last thing to notice is that this one and this one are like terms. They're the only ones that have the same base. So this is going to end up being w to the second power I'll put b to the fifth minus 8 a to the 11th k to the fifth all over p to the third power. Right, so everybody stayed in the same spot except for this guy. It's the only one that flipped, not flipped, but we ended up with our rule of b to the fifth minus 8, which gives you a negative 3. Right, this guy's going to end up being equal to negative 3. And so I'm going to move it back down to the denominator, and so we'll end up with w squared a to the 11th, k to the 5th, all over b to the positive third power, p to the third power. Good? Questions? No? Okay, so that's one of the curiosities we get. The other one is this. If I had 3 to the fourth power divided by 3 to the fourth power, what should that be? 1, right? They're identical, they cancel each other. Or you can expand it all out and see that 3 times 3 times all of it expanded all out, everything cancels, so we get a 1. Or if we use our properties though, 3 to the fourth power over 3 to the fourth power, according to our second rule of quotients, this must mean that it's 3 to the 4 minus 4, or 3 to the 0. Oh, okay, so again, how do we deal with this? We make it equal to that. Defined to be the same. Defined as the same. Okay, so that means that 3 to the 0 power equals to 1. Well, there was nothing special about the 3 or the 4. We can do that with any number, right? Any number you give me, 18 raised to the power of 2.785 over 18 to the power of 2.785. I have no idea what that is. It looks pretty ugly, but they're identical, right? That's the important part. They both look exactly the same. I know they're going to cancel to give me a 1. Right? Okay, and then following my rule, I get that this is 18 to the 2.785 minus 2.785. Oh, that's just going to be 18 to the 0 power, which equals to 1. Okay, so it doesn't matter what numbers you use, it's always going to be true, which is why any number raised to the 0 power is always 1. What's 2.7 to the 0 power? 1. What's 3.45 raised to the 0 power? 1. Right? What is the number pi raised to the 0 power?
1.
1. Right? It doesn't really matter what that value is, there's only one catch. Right? As usual, thou shalt not divide by 0. So the only thing that base cannot be is a 0. So the only thing we can't deal with right now is that. 0 to the 0, right? We can't let that base be equal to 0. But other than that, for any other value, b raised to the 0 power is always 1. So that's what that rule says. B to the 0 power is always equal to 1, as long as b itself is not 0. 0 to the 0 is more complicated. Armed with that, we can take a look at some of these guys. How do we simplify this one? So what's the answer going to be?
9
Over
b to the power of 7.
9 over b to the power of 7, right? Very straightforward. So that's this one. 9 over b to the power of 7. What about number 2? What do we do with this guy?
So it's b to the power of 5
5 times b cubed, right? We just move it up. Notice it's not a reciprocal. If it was a reciprocal, the 5 would have gone down to the denominator, and it didn't. We just moved this b up to the numerator. All right, what about the third one here? Okay, well, we can deal with this individually or separately from this guy because we have an addition there. So this guy by itself, how do we simplify it? 1 over 3. And what is this guy going to be? 1 over 4.
So then we have to deal with the sum of 1 over 3 plus 1 over 4. We have 3 to the negative 1 plus 4 to the negative 1. I know this is 1 over 3 plus 1 over 4, right? Because of our rule of negative exponents. So now we just got to make sure we get a common denominator. What's it going to be in this case? 12. So I'm going to multiply this fraction by 4 over 4. Multiply this fraction by 3 over 3. Which gives me 4 over 12 plus 3 over 12. I know my final answer is going to be 7 over 12. Okay, so let's work on these guys. How do we simplify number 1 here? We got 3bc to the 5th power, the whole thing being raised to the 2nd power. So that'll be... Oh, we have to be real careful here, right? Because this guy has a 2 here, and this guy has a 3 here. For that reason, we cannot play with these guys first. We have to deal with the exponents first. So you can't really cancel out the c's and deal with the b's at this stage because they have different exponents. Now over here on the second example, we will be able to do that because it's all one big happy fraction raised to the same exponent. So that's why you're able to do it here. But here we're going to have to distribute first. So when we distribute, we'll end up with 3 to the 2nd power, which is 9, b to the 2nd power, c to the 10th power, and down in the denominator we'll end up with 8, b to the negative 6, and c to the positive 6. Okay, once we do that, then we're able to simplify them. So I end up with the b's, I ended up with a b to the 2nd in the numerator and a b to the negative 6 in the denominator. So to bring them together, it'll be b to the power of 2 minus negative 6, which is what we get here. Okay, so following around the distributions, we ended up with this, 9, b to the 2nd, c to the 10th, and then 2 to the 2 to the 3rd power was 8, and then b to the negative 2 was negative 6. Okay, and then c to the 6th power there by multiplying the 3 and the 2. Okay, and so now using our rule of quotients, this becomes b to the power of 2 minus negative 6. And now it's kind of a plus plus rule there. So we got to bring those together to give me b to the 8th power. And then the c's, we end up with c to the 10 minus 6, which gives me c to the 4th power. All of that divided by 8. Good? Any questions? Any questions? Any questions? Any questions? No. Okay, in the second one, now it really benefits us to simplify this first and then deal with the exponent. So if we reduce, we end up with 3. Now here, we have to be careful about our rule because we end up with b to the power of negative 4 minus negative 3 and c to the 7th minus 2. And all of that's still raised to the power of negative 4. So the number is reduced to just 3 up in the numerator. And this becomes b to the power of negative 1. Negative 4 minus negative 3 becomes negative 4 plus 3, or b to the negative 1, c to the 5th power. And we see that here. Okay, so in the on the inside of the parentheses, we end up with 3. b to the negative 4 minus negative 3, c to the 7 minus 2, which then reduces to 3, b to the negative 1, c to the 5th power. All of that is still being raised by to the power of negative 4. Shut up, Microsoft. Power of negative 4, which then gets distributed. We get 3 to the negative 4, b to the negative 1 times negative 4. That's just going to become b to the positive 4, c to the negative 20th. Good. So now we just got to get rid of these negatives in the exponents. We bring them down underneath the fraction to the denominator, and we end up with this, and then the 3 to the 4th power becomes 81c to the 20th. Good. Questions? Yeah.
So that 3 to the negative 4 is the only one that doesn't have parentheses?
3 to the negative 4. Oh, this.
No,
3 to the negative 4?
Right above
Yeah.
Now that those have the tendency to be -1 and c to the fifth. So only the 3 to the -4 doesn't have it.
Okay. So the reason why are these extra parentheses here, and how come this one doesn't have it?
Just 'cause it's a number?
Well, it's because this has an exponent raised to another exponent. So they're just pointing out that when we distribute here, you have to multiply the -4 times the 5, the -4 times the -1, and while this 3 doesn't have an exponent, doesn't have one explicitly written, by default, if there's nothing there, we know it's an exponent of 1, right? But it just seems cumbersome to have to write it in there. So that's the only reason why they have these extra parentheses in there, to remind you that you still have to have an exponent raised to another exponent and multiply it. Good? Questions, comments, issues?
Okay, so an exponential function is a function whose equation can be put in the form f of x equals to ab to the x power. Or, if the f of x bugs you, you can always think about putting back that y. Y equals to ab to the x power. So let's explore what that general function means. So remember back when we were with linear equations. With linear equations, we found that the general form, one general form for a linear equation is y equals mx plus b. This is where the m and the b are allowed to be any real numbers. So examples of this general form of a linear equation are when m is 3 and b is 5. For instance, this is a case where the m is a 3, b is a 5. Or y equals to -2x minus 7. Or y equals to 2.3x plus 9.5, or so on and so forth, right? So there's all kinds of examples of linear equations we can come up with where all we do is change the m and the b, okay? So when we graph these, we see that these two things, as they move around, they will change the line and give you different lines. So for example, let's think about this one. Here is the line y equals to mx plus b, where we have the freedom to move around the value of m. So currently m is set equal to 1, and the b is set equal to 1. So right now, this line over here is representing the value y equals x plus 1. And as we move around the m, so if we make m a little bit larger and becomes 1.3, 1.7, 2, 2.5, 3, 3.4, so like at this point, this is the line that is being represented by y equals to 4x plus b, where b is 1, so 4x plus 1. So as we see, as we change the m to make it a larger and larger positive number, the slope gets steeper in the positive direction, or back to 0. 0. And then as we go into the negatives, it turns into a negative slope in this direction. So this is negative 0.7 slope, negative 1.3 slope, and so on and so forth. So we can see that the pitch, the angle, the steepness, the slope of the line is affected this way. And notice that in every one of these cases, as we slide around the value of m, it always crosses the same point of the y-axis at 1. Right? So the m determines the steepness of the line, and then the b determines where it crosses. So it shifts it up or down as we move that value. Okay? So almost all lines can be described by a particular choice of m and b. Right? Given any line, with only one exception, the vertical lines, right? Vertical lines can't be described this way. They're the only unique things. But other than vertical lines, any other line can be described by two things: the angle, the pitch, the angle, and where it crosses the y-axis. Okay, so those are lines. But now we're going to be working with a different kind of an equation, an exponential one. So now we're dealing with this. We have something that fits the form of y equals to ab to the x power. So this is the general form of an exponential. And we can also write it in the form of f of x equals to ab to the x power. Right? So this is where the a and the b are different values. So keep in mind that we still have this as the dependent variable. dependent variable, and the x is still the independent variable. Right? So also we can think of it as the input. This is the value we are inputting into our equation, and this out here represents the output, the answer when we input a particular value. The a and the b are kind of like the m and the b here. They're constants. So when we plug in a number into the a and the b, then we get a particular choice of an exponential function. So for example, we could have a function described as, or an equation described as y equals to 3 times 2 to the x, for example. So here the role of a is being played by an a, the role of b is played by a 2. Or we can have another one like this, how about 5 times 2.3 to the x power. Here the role of a is being played by a 5, and the role of b is being played by a 2.3. Okay, so we can have different choices of a and b to be able to generate the exponential equations or exponential functions. Good? Exponential equation with the y, and then when we write it in this style of notation, then it's a function. Function notation. Good? Any questions? Any questions? Any questions? Okay, so the definition, an exponential function is a function whose equation can be put into the form f of x equals to ab to the x power, right? So something like this, here's a function. However, we do have some restrictions on the a and the b. When we were working with linear equations, we really didn't have any restrictions on the m and the b. They could be anything, zeros, negatives, it doesn't matter, decimals, big numbers, small numbers. There was really no restrictions on the m and the b. However, we will have some restrictions on the kind of choices we can make for a and b. So, for starters, the a is not allowed to be 0. That's just because if we let a equal to 0, then it's just a really boring equation. If we let it be equal to 0, then no matter what happens, 0 times anything is 0. So this part just becomes silly, right? If it was 0 times 2 to the x power, well, the answer is always 0. So it just becomes a boring answer of f of x equals 0 or y equals 0, which is just going to be a linear equation, right? It's just the horizontal axes, right? Y equals to 0. So we choose not to allow a equal to 0 because then it becomes boring. Same thing happens when we allow b to be equal to 1. There's nothing wrong with it, it just becomes boring. Because if we think of that case, if we have y equals to 0 times b to the x power, well then that's just boring because no matter what you choose for x, right, no matter what b is, no matter what x is, the answer is always going to be 0. Good? Let's choose a particular, like for example, if this was 2 to the x power, well then that's just going to be 0 and it just becomes kind of boring. On the other hand, if we choose b to be 1, consider y equals to 3 times 1 to the x power. Well, 1 to the power of anything is always 1. So again, it just becomes kind of boring. That guy right there is always going to be 1. So this just simplifies to just that, which is again another horizontal line at y equals to 3. So these two cases of a equals to 0 or b equals to 1 are just too simple, too boring, simplistic. It doesn't fit the pattern of the rest of them, so we just intentionally ignore them. And the other thing that we want to avoid is letting b is not allowed to be a negative number, and it's got to be a number greater than 0. So a positive number greater than 0, we will see why that is in the next section, but for now, we just got to keep that in mind. So these are the conditions. A is not allowed to be 0. B has to be a positive number bigger than 0, so it's not allowed to be 0. And a B is not allowed to be 1. So those are the conditions on the A and the B. As long as you keep those conditions in mind, then the A and the B are allowed to be any real number. Here we have a couple of functions. F of x equals to 3 times 2 to the x power, and g of x equals to 5 to the x power. Find some of these statements. So the first one is find f of 3. The fact that it's got an f on there lets me know that I gotta look at the f function, right? I got two choices. I got f of x equals to 2 to the x power, and g of x equals to 5 to the x. But I know that f of 3 is talking about the f function, So I know that this is going to be 3 times 2 to the third power, where this 3 is going right in there, right? That's the input value, replacing the x. And now we just got to simplify that. So from earlier, we remember that this must be, this 3 only applies to the 2. So this must be 3 times 8, which is equal to 24. Good. What about the second one? F of negative 4 is equal to 3 times 2 to the negative 4 power, which is 3 times, how do we deal with the negative in the exponent?
Put it in the denominator.
Put it in the denominator, 1 over 2 to the 4th power. Okay? And so what is 2 to the 4th power? 3 times 1 over 16, which then is just going to give me a final result of 3 over 16. Good? Questions, 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 questions? No, 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 no. Good. What about the next one? What is g of a plus 3 equal to? So now we got to go over to the g instructions. And the g instructions, the g function is 5 to the x power, which is 5 to the a plus 3. Right? So the independent variable is replaced by that guy right there. That's what goes up there. And now we want to simplify that a little bit. And if you remember our rules, look at that first rule up there. If there is an addition up in the exponent, that's equivalent to a multiplication of 2 exponential numbers with the same base. So we can separate this as 5 to the a power times 5 to the third power. Good? And why would we want to do that? Well, this is something we can actually multiply. Right? 5 times 5 times 5 is 125. And now if we just flip these around, we'd get 125 times 5 to the 8th power. Okay. Now be careful there's enough space there and then you've really clearly identified that there's a multiplication there. Because if you do this the wrong way, someone might look at this and go, oh look, it's 1,255 raised to the power of a. Right? So we have to be careful. So you can either be really neat and separate them and put a little dot there, or you could put a parentheses there. That way it's clear that the a only applies to the 5, for instance. So that's just one of those little things you got to be careful with notation. Questions, 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 questions? Yeah?
From there on, can you still multiply the 125 with the 5 to the 8?
No. So the a only applies to the 5, so we got to be careful to leave them separate, because if you did multiply the 125 and the 5, then you're saying that the a applies to the 125. So it's not true that we can do that. Same thing over here when we did this one. This negative 4 only applied to the 2. So that's why we flipped it and wrote it as 2 to the 4th. So common mistakes are this. People try and do 6 to the negative 4, and then they go like this, 6 to the 4th, right? So that's not true, because you can't multiply it first, because if you multiplied it first, that would mean that this is part of that, right? If this is what we intended, then you should have written it this way, or they should have given it to you this way. 3 times 2 raised to the negative 4, right? And then it would apply. But, you know, why would anybody give it to you that way? 3 times 2 raised to the 4, that's just 6, right? So it seems like unlikely you'd ever see it that way anyway. Okay? G of 2a, well that's going to be 5 to the power of 2a. And again, if we go back to our rules, then that bottom one down there, we get that if there's a multiplication up in the exponent, that means that we could rewrite it as an exponential number raised to another power. So I could rewrite this as 5 raised to the power of 2, and the whole thing raised to the power of a. 5 squared raised to the power of a. Right? Because our rule tells us that if we have an exponential number raised to another exponent, we multiply the exponents. But in this case, we want to write it this way so that we can express it like that. Good? Any questions? Any questions? Any questions? One thing to be really careful about, one of the most common mistakes you'll run into is that people confuse 2 to the x power and 2x all the time. So it's worth spending a couple minutes seeing the difference between the two of those so that you guys don't make that mistake. So the first one, we have y equals to 2x, or we can write it in function notation of f of x equals to 2x, right? Either one, we're looking at that one. Okay, so this is a linear equation with the slope of 2 and the y-intercept of 0, okay. This is saying that when you give me an input, the output, what do we do to the input to get the output? What's an easier way of describing this in terms of input-output? How about double your input equals the output equals double the input? Whatever you give me, I'm going to double it, right? That's what this is describing. So let's look at a little table with some results. How about x and, let's go back to x and y notation for an equation. So if we input it as 0, what do we get? 0. Double the input, we still get a 0. Double 0 is, twice 0 is still 0. 1 will result in a 2. 2 will result in a 4, right? 3 will result in a 6. 4 will result in an 8. 5 in a 10. So we get the idea. Negative 1 is negative 2. Negative 2 is negative 4. Negative 3 is negative 6. Good? Okay, what about the other one? Well, this one is y equals to 2 to the x power. So when you input a value, this isn't doubling your input. You're saying the input value is how many copies of how many factors of the 2 you're going to have, how many multiples of the 2 you're going to have. So we can write this in function notation as 2 to the x power. And as far as a little table with some examples going back to the x and y, well, if we typed in, let's say 2 in there, we end up with 2 to the second power, which is 4. And if we typed in a 3, we would get 2 to the third power, which is 8. And 4 is 2 to the fourth power, which is 16. Okay, what about in the other direction? Okay, so we get a 1 there. Well, that one's easy. That's just 2. What about 0? 2 to the 0 is just 1. Okay, so 1 leads to 2, 2 leads to 4, 3 leads to 8, 4 leads to... Right, so it's growing by multiples of 2. We're not doubling it. We're growing by multiples of 2. And in the other direction, if we put in a negative 1 there, we'll get 2 to the negative 1. And how do we deal with negatives in the exponent? We put it underneath 1. So this is equal to a half. 2 to the negative 1 is equal to 1 over 2. To the positive 1 power, if you like. What about negative 2? 2 to the negative 2, which is going to be 1 over 2 to the positive 2 power, which is equal to 1/4. Good? Negative 3, well, we see the pattern that's happening there. So we don't get a negative answer when you input a negative number, we get a fraction. A fraction where the numerator is always 1 and the denominator is going to be equivalent to the result we got when we had a positive number plugged in. So I know that this is going to be equal to 1 over 8, right? Because that one was an 8. And I know that the next one, negative 4, is going to be 1 over 16, then 1 over 32, then 1 over 64, and so on and so forth. So what the pattern we see is that as these numbers grow toward the negative infinity direction, so they're getting larger in the negative direction, they're growing toward negative infinity, then the results are getting smaller and smaller and smaller, right? They're fractions that are getting closer and closer and closer to 0, but in fact they never actually equal 0, right? We're going to have fractions that are like 1 over 8, 1 over 16, 1 over 32, 1 over 64, so on and so forth, right? And that denominator can grow really big, but it'll always be 1 over a number that's really big. So it'll get really close to 0, but never actually 0, right? And also, none of these answers are ever going to be negative, right? Because if I plug in positive numbers, the answer is positive. And if I plug in negative numbers, the answer is a fraction that's positive, a positive fraction. Good? Good for you? Okay, so two very different equations, but people confuse these all the time, so just kind of take a minute and think about it. Let's graph them and see how they compare.
Okay, now let's take a minute and look at the graphs of y equals to 2 to the x and compare that to the graph of y equals to 2 to the power of x. Let's begin by creating a table and graphing some ordered pairs. We can look at the pattern there and then look at the overall graph. So if we start with y equals to 2 to the x, let's come over here and create a little table for that function. So if we type in 0 equals to x, then y is going to be equal to 2 times 0. We're doubling the input. So double 0 is still going to be 0. So we have the first ordered pair of that equation, y 0 comma 0. And as you can see, that's this little dot right here, right at the origin, 0 comma 0. If x is equal to 1, then when we double it, the result is going to be 2. So we get this ordered pair right there, 1 comma 2. Then if we put in a 2, then we double the input, we get a 4. If we put in a 3, we double the input, we'll get a 6. Put in a 4, double the input, we get an 8. Now, it doesn't have to be just integer values. Those are just nice, convenient results that we often refer to. But that leads to this idea that perhaps we can only put in integer values. But we can also put in decimal values. Like if we typed in 4.672 and doubled that, we would end up with 9.344. And that would also work out. So that would be this ordered pair up here. Okay? So we can also type in some negative numbers, like negative 1. Double that leads to negative 2. Put in a negative 2. Double that equals to negative 4. How about negative 3.5? Double that, that leads to negative 7. Negative 5.25. That's going to lead to negative 10.5. As we can see, that's this guy right down here. Okay, so as we can see, these points seem to line up. And if we kept doing this over and over and over and over and over an infinite number of times, there would be so many points, they'd be so close together that they would begin to look like a line. They would begin to look like that line right there. Right, so all these ordered pairs all fall into this red line, which is the line y equals to 2x. Good, okay, so now let's compare that to y equals to 2 to the x power. So again, let's create a table. Let's begin with 0. We all know that 2 to the power of 0 is equal to 1. So we get this little green dot right here. This one belongs, is a point on the equation y equals to 2 to the x power. Now if we let this be equal to 1, then we get 2 to the 1 power, which is 2. If we let this be equal to 2, then this becomes 2 to the power of 2, which is 4. We let this be equal to 3, then we get, well, this is 2 to the power of 3, which is equal to 8. 4, well then this goes to the power of 16. 2 to the power of 4 is 16. And, well, as we can see, this thing is just growing pretty quickly. Already when x equals to 4, the result is off the charts over here. I'm going to have to zoom out a little bit just so we can see. There it is. So 4 comma 16. Okay, so as we can see, these green dots here are beginning to form a different shape than the purple dots did. Let's look at some negative results. So if we type in a negative 1, then this is going to be 2 to the power of negative 1. And 2 to the power of negative 1, the way we deal with that negative 1 is to flip it underneath 1. So this whole thing becomes 1 over 2. 1 over 2, or 1/2. And so that creates this little dot right in here. Right, negative 1 comma 0.5. Let's zoom in to there because we're going to get a bunch of fractions. Okay, so I zoomed in quite a bit. So here's 1, and then halfway between 0 and 1 is a half. And so when x is negative 1, the result is negative 1 comma 0.5. Now when x is equal to negative 2, then this is 2 to the power of negative 2. And as we know, the way we deal with that negative there in the exponent is to flip it underneath 1, make the exponent positive. So that's going to be equal to 1 over 2 to the power of 2, which is going to be 1/4. And that's what we get here. 1/4 is 0.25. And so this is negative 2 comma 0.25. Okay, so then let's keep going over here. If we typed in a negative 3 here, then this becomes 1 over 2 to the power of 3, which is 1/8. And this is negative 4, 2 to the power of 4. Okay, so as we can see, as we type in negative numbers, they go larger and larger, into closer and closer to the negative infinity side. As x grows in this direction, then the resulting values of our equation are going to be 1 over a power of 2 that keeps growing in magnitude. And so the overall fraction is going to become smaller and smaller, closer and closer and closer to the x-axis, but never actually equal to 0. Also notice that we're never going to get a negative result. Okay, so let's zoom out a little bit again. And so again, if we kept graphing more and more and more of these green dots, let's try another one. How about negative 8? 1 over 2 to the power of positive 8. We get that one. It's so incredibly close to the x-axis that it looks like it's on the x-axis. But if we zoomed in, we'd see that it's not actually on the x-axis. There, we see that in fact it isn't really on the x-axis. Okay, so if we did this over and over again and eventually graph so many green dots that they would be really close together and eventually they'd form a shape that looks like this. Okay, so clearly these are two very different equations with very different input-output pairs and then very different graphs as a result.